Hi, everyone. Time to do some combinatorics together. Always an exciting time. So let's recall where we've been and look a little bit at where we're going to be going next. So remember, we were looking at two colorings of the square. Okay. One thing that I would say to you is, again, we're looking at this example in a lot of detail. But in general, what we do here will actually extend to other more complicated situations, where we might have a shape that has lots of vertices, lots of edges, and we'll be able to describe certain kinds of motions that move some of these shapes into other ones. We call these symmetries of those shapes, and we'll also have more colors to color the vertices with. Okay. And I'll remind you that we were interested in, okay, we want to have some rigorous notion of which among these colorings are equivalent to one another. And we grouped these into 6 groups, these 16 colorings into 6 distinctive groups. And the equivalence, we said, had to do with various ways of moving these shapes around in 3-dimensional space, either flipping them over, i.e. reflections, or rotating them around. Okay, those are rotations. And we said that there are exactly 8 of those rotations and reflections. And then last time we made an argument for why it is that there couldn't be any more. Because you might imagine in your mind that, for instance, if I were to combine a rotation and a reflection, that I might end up with something new. But that just simply is not true. Okay. That's all there is. In fact, we said that if you have an even number of edges, we showed it for an even number of edges, but it turns out it's also true for an odd number of edges and vertices, like for a polygon with in vertices and in edges, that you're going to have in rotations and in reflections. Okay, and those are really all that there are, because if you think about any vertex and an edge like in the clockwise direction coming off that vertex, that vertex has n possible places it can move to, and its edge, all it can do, that edge you're paying attention to, all it can do is flip to one side or the other. Okay, so there are 2n possible places that vertex and edge can go. And that means that there are a total of 2n total symmetries at most, or actually at least 2n symmetries. And or actually at most, but we've already found 2n of them, so that means there are exactly 2n symmetries. And remember the rotation part, the fact that there are n rotations is pretty obvious. There are exactly n places I could kind of rotate this thing around a vertex. Now, what about reflections? Well, in the even case, we matched up opposite vertices or opposite edges. Matching up opposite vertices gave us n over 2 reflections, and matching up opposite edges gave us n over 2 reflections. Okay, but in the odd case, what you do is you basically, if you imagine sort of a pentagon, and I think they actually have a picture of this somewhere. Let's see. I think there's a pentagon. Yeah, here it is. So here's a pentagon. In like the case of an odd number of vertices and edges, polygon with an odd number of vertices and edges, of course you can match up an edge with a vertex on the opposite side. Okay? And there are n possible ways to do that. And each one of those, you kind of draw an axis of reflection through that vertex and that opposite edge. And there are a total of n of those. So you're going to have n reflections and n rotations for a total of 2n. And again, the same argument works for why there couldn't be any more, because you just think about possible destinations for a fixed vertex and its clockwise edge. And there are n possible destinations, and then the edge could be flipped around or kept on the same side, the clockwise side, for a total of at most 2n symmetries. Okay, so we're not missing anything here is basically what we were saying, right? Here was a picture of all the different things once we labeled them. Okay, we were using A, B, C, and D, and also we could use numbers if we wanted to label the vertices. But these were all the different symmetries of the square. And one thing I wanted to point out here, though, is this notion of trying to figure out which of these colorings are indeed equivalent needs to be made rigorous. Just like we had to make the notion of moving things around, moving these shapes around and preserving the shape, we had to make the notion of symmetry rigorous by introducing permutations, and we were able to pull that off by labeling the vertices with A, B, C, and D, or 1, 2, 3, and 4. And then thinking about, okay, permutations we've usually thought of as words in one line array notation. But then we said, really, it's a function from like 1, 2, 3, 4 to 1, 2, 3, 4. And we can illustrate that by writing it in two-line array notation. Okay. And then we can also write down a cycle structure for the permutation. So we had those three different notations for a permutation, namely one-line array, two-line array, and cycle notation, cyclic notation. But this notion of which colorings are equivalent to one another is tied to a concept that you probably have seen in multiple of your math classes called an equivalence relation. Okay, so essentially what we're going to describe through these symmetries is ways that we can move one coloring into another, right? So if I can rotate one coloring into another, we consider those to be equivalent colorings. Or if I can reflect one coloring into another coloring, we consider those to be equivalent coloring. And remember, we were using the little twiddle symbol or tilde symbol to say that two colorings were equivalent. Now, I just want to remind you what an equivalence relation says. Okay, so we have a set of elements. In this case, it's colorings. And we write A twiddle B, right? That means they're equivalent. If they're equivalent. And it has to satisfy three things. First of all, every element has to be equivalent to itself. Clearly, that's true for the colorings of the square, right? Every single coloring is equivalent in the way that we're thinking about it to itself. Symmetry, that is, if one element is equivalent to another, then the second element is also equivalent to the first. Now that might seem kind of like a duh, but that's not always true, okay? For a relation, okay? So that's why it has to be symmetric, because it needs to behave like equals, basically. And then the transitive property, if A is equivalent to B and B is equivalent to C, then A is equivalent to C. It's behaving like equals. It's called the transitive property. You can see why that's true for colorings. If one coloring, so like if I go up to this picture up here, coloring 2 is equivalent to coloring 3, okay, and coloring 3 is equivalent to coloring 4. Okay, both of those equivalences I just stated is gotten at through rotation by 90 degrees in the clockwise direction. Then the transitive property says C2 should be equivalent to C4. And it is basically by just applying the 90-degree clockwise rotation twice, or you could just apply the 180-degree rotation. Okay. So I just wanted to point out that, equivalence relations are pertinent here. And in particular, the concept that we're talking about when we say, colorings that are equivalent, those are the so-called equivalence classes. Okay, the kind of blocks of elements in the set of colorings that are all equivalent to one another. Okay, we called those equivalence classes when we talked about equivalence relations generically. here's some basic examples of equivalence relations. You know, for a set of people, being the same weight is an equivalence relation. All people of a given weight form an equivalence class. Okay, so there you go. That's one way you could break up the collection of all people into equivalence classes. Okay, for a set of numbers, differing by an even number is an equivalence relation. Okay, differing by an even number is an equivalence relation. So if two numbers differ by an even number, then both the numbers are either even or both the numbers are odd. So what that tells you is there are exactly two equivalence classes here, the odd numbers and the even numbers, okay? But that's, I mean, right, that's if we're talking about integers. For a set of figures, having the same number of corners is an equivalence relation for each n. So those are just a couple of basic examples, okay? All right, so what I wanted to do was, let me share this screen here. And I wanted to, first of all, just as an opening exercise here, I wanted to actually oops. Okay. So let me see here. I wanted to actually go in here and do and look at some of those. I wanted to look at some of those permutations. Okay, so remember we had pi 1. Okay, so pi 1. What did pi 1 basically do? Well, nothing. A, B, C, and D. All it did was basically sent each one of these to themselves. Okay. There we go. What did pi 2 do? Pi 2 was 90-degree rotation. So pi 2 was 90-degree clockwise. Right, so clockwise rotation. Okay, pi 3 is 180-degree rotation. Pi 4 was 270-degree rotation. Of course, 360-degree rotation, that's basically pi 1. So, you know, just as an example, or just to kind of, you know, get our juices flowing a little bit. So how would I write pi 1? Pi 1 is a one-line array permutation, okay? I'm going to use letters this time instead of numbers, but same idea. So in one-line array notation, where does A go? Well, to A. Where does B go? To B. C goes to C, and D goes to D. So I write that way in one-line array notation. In two-line array notation, it's A, B, C, D. Where does A go? A, B goes to B, C goes to C, D goes to D. So there's two-line array notation. And then what about cycle notation? Well, cycle notation, what you do is you basically follow a cycle in the two-line array notation. So A goes to A, okay, and then you're done. So like in the cycle notation, you would just go like this. Okay, each element here kind of forms its own cycle. Okay, what about pi 2? That's a little bit more interesting. And I'm not even going to draw the picture because I want to have to think through this. Okay, where is A going to go? Well, to B. B goes to C, C goes to D, and D goes to A. Well, hang on a second. Up here, I'm sorry. A, B. Okay, A, B, C, D. Sorry about that. That was a little typographical error. Okay, A, B, C, D. Okay, so what about this? So A goes to B. That's why in the first position, that's the image of A. B goes to C, C goes to D, and D goes to A if we're in pi 2. Okay, so in two-line array notation, this would be A goes to B, B goes to C, C goes to D, and then D goes to A. And you kind of follow that around when you want to give the cycle notation. So it's going to be A goes to B, and that goes to C, and that goes to D, and D goes back to A. Remember, we go like this. We just kind of watch where things are mapped under this permutation. Okay, so A, B, C, D. And I at least want to do pi 4 or pi 3. Okay, so let's do that. Okay, so pi 3, that's 180-degree rotation. So that means that A is going to go to C, B is going to go to D. Okay, where does C go? Right, the third position is the image of C. Where does C go? Well, C goes to B. Okay, or actually, no, sorry about that. Okay, C goes to A. Okay, because of C, D, A. Okay, and then where does D go? Well, it goes to B. Okay. You know that you will have made a mistake in the one-line array notation if you have repeated letters, okay, because you should have every single letter being there exactly one time. Okay, in the two-line array notation, A went to C, B went to D, C went to A, and D went to B. Okay, and in the cycle notation, what do I have here? AC, A goes to C, and then where does C go? C goes back to A, right? So it went boop, boop, like that, okay? And then secondly, what happened? Well, B went to D, and D went back to B, okay? All right. So, let me stop doing that, okay? All right, so let's go back into here, and we'll keep on trucking here. Okay, so there we go. So we explained why the number of symmetries are what they are last time. Okay, I wanted to talk about the case of the tetrahedron a little bit, because that's something that we're going to be acutely concerned with later on. Okay, what about the tetrahedron? Well, okay, a tetrahedron consists, okay, first of all, what is a tetrahedron? Well, it's just 4 equilateral triangles, stacked to form that pyramid shape. Okay, it has a total of 4 vertices and 6 edges, if you want to think about it as kind of as a graphical object. Okay, so one thing that you can do is you kind of have rotations of symmetry, in the sense that you can put an axis through any vertex through to the triangle, the center of the triangle on the opposite side. And you can simply spin that thing around on its axis, okay? And it's going to have a total of, 1, 2, 3, and you're back to the beginning rotations that go around like that. One of those is the identity. One of those is rotation by 120 degrees. One of those is rotation by 240 and then 360. Now there's also kind of a funny, unobvious one as well. Namely, you can kind of take the tetrahedron and you can put an axis through the middle of one of the edges and then go down through the middle of the tetrahedron to the edge on the opposite side through the middle. And then what you can do is you can rotate that thing by 180 degrees and you can spin that thing like that. Okay, so that's kind of interesting as well. Okay. So first of all, how many rotation things are there? How many rotation things are there? Well, I have a 120 and a 240 degree rotation for each one of the vertices paired with an opposite face triangle. Okay, so that gives me a total of 8 of those. Of course, I also have the trivial identity that doesn't do anything to this. Okay, And then how many of these things right here are there where I have, you know, an axis of rotation where it's basically through one edge and then through an edge in the middle on the opposite side? Well, there's a total of 3 of those because you just pair up opposite edges. There's 6 total edges divided by 2 for each one of those pairs. It's 3. So there's a total of 12 symmetries for the tetrahedron. So that's kind of interesting stuff right there. And they have they've listed both types of those symmetries right there. So that's good stuff. Okay. All right, so here is where they started talking about cycles, and I want to go into the presentation that I've given you, just so that we can talk through some stuff. And by the way, look at this thing right here. So pi 7, what was pi 7? Pi 7 was basically reflection in the negative slope axis. Reflection in the negative slope axis, I think. Let's just check real quick. Okay, pi 7 was reflection in the negative slope axis, yes. Basically put an axis through A and C, and you reflect B and D back and forth. So that's why they have this cycle structure down here. The cycle structure down here that they do. BD flips back and forth in a cycle, see this? And A and C are just all by their lonesome right here, okay? Hopefully that kind of makes sense. Now, this part right here is where I start to get a little nervous with some of the notation, because they're not, okay, you have the permutations themselves, which you write like this, but then in my opinion, they kind of murky the waters by writing pi 3 equals to this junk right here, okay? Pi 3 itself, right here, ACBD, it induces kind of a permutation on the colorings. So like, what does pi 3 do to coloring 1? Okay, so what is this saying? What does pi 3 do to coloring 1? Okay, pi 3 is the thing that just flips A and C back and forth. The two, that kind of flips the diagonals back and forth among each other. Remember, C1 was that coloring that had all the same colored vertices. I think they were all either black or all either white. We'll look at that in just a minute. But what this thing is, what this thing is doing is it's actually going through all of the colorings and actually seeing which coloring goes to which coloring. So C2 going to C4, for instance. Let's see that up there if I look at those colorings. Okay, C2 going to C4. Well, what I have to know what C2 is. C2 is this guy right here that you have one white vertex in the upper left. C4 has one white vertex in the lower right. Okay, so C2 and C4, does the coloring that kind of flips both diagonal vertices around? Yes, that's going to toggle between C2 and C4. Similarly, C3 and C5 are going to toggle between each other. What about C6 and what about C6? Well, that's going to toggle between, think about it, if in C6, you're going to flip the 2 diagonals around, and you're going to flip the two other diagonals around, and you get to C8. So C6 and C8, C7 and C9 are kind of in a little cycle with each other. C10 and C11, what's funny about those is those are just going to themselves under that permutation. And C12, well, C12 is going to flip back and forth between C14. And C13 is going to flip back and forth between C15. Remember, we're flopping both diagonals. C16 is going to be itself. So C10 and C11 are itself, go to themselves. C16 goes to itself, and C1 goes to itself. But all the other ones are in little cycles of length 2, and they're kind of off. The indices are separated by 2 each time. So let's go down here and just make sure that that's true, just so that we can have peace of mind here. Okay. C1 goes to itself, C2, and C2 goes to C4, and C4 goes to C2. C3 and C5 flip back and forth. That's what that 2-line array notation is saying. C6 and C8 flip back and forth, so do C7 and C9. As we said, C10 and C11 are going to be fixed. C12 and C14 flip back and forth, so do C13 and 15 and C16. Now, the reason I don't like the fact that they are identifying pi 3 with this is like this isn't even a permutation of the same number of things. There's 16 things right here. This is the permutation. This is the permutation, okay? It's a permutation of 4 elements, not 16. But this permutation induces a permutation on the colorings. So I would rather they used a different notation. Okay, so all that to say, you know, we're starting to get to a place where we can talk rigorously about these things, but there are some notational concerns that I have that are going to show up when we go over into the notes that I've given you. Okay. So let me see here. Here we go. Okay. Hang on a second. Here we go, right here. There it is. Okay. So what I have chosen to do, and you should, I hope you'll understand why I'm doing this. Pi 2 is rotation by 90 degrees. Okay. And that will induce, which means that like A goes to B, B goes to C, C goes to D, and D goes to A. Okay. Or you can, if you wanted to use numbers, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes back to 1. But that induces a movement of colorings, okay? C2, what if I rotate that by 90 degrees? Well, nothing, it just stays by its lonesome. Well, but C2 goes to C3, C3 goes to C4, C4 goes to C5, and C5 goes back to C2. Remember that was that grouping of 4 colorings we had above. And then you see that C6 goes to C7, which goes to C8, which goes to C9, and C9 goes back to C6. C10 and C11 rotate into each other, okay? So they're in a little cycle. Same thing with C12, 13, 14, and 15. They're in a little cycle, and C16 is fixed by 90-degree rotation. And so you can even write this thing in cycle decomposition. But again, this is not the same as pi 2. The book muddies the waters by saying that, or by writing them as the same thing. It induces this other permutation. So I'm kind of, you know, obsessing about that. Okay. So, and the other thing that the other problem that I have with some of this permutation stuff is they kind of muddy the waters in terms of what it means to actually apply 2 of these things. They always want to read the permutation from left to right. And by the way, right here I'm saying pi I, pi j. That means first apply pi I, then apply pi j. So like maybe I apply a reflection first and then the rotation. So you apply these things in a left to right direction. Then the permutation corresponding, or the color-induced permutation corresponding to that is the same as what I would get if I kind of took the coloring ones and operated them together. Okay. So what about pi 6? What is pi 6 doing? Pi 6. So what is pi 6? Okay, so pi 6 is reflection in the horizontal axis. Okay, so it's going like this. Pi 6 is reflection in the horizontal axis. So A is going to D and B is going to C. It's going just back and forth like this. Okay. And I mean, I'll let you work out the details here, but it ends up being equal to this thing. And I'm telling you, so what in the world do we mean by this? This is where I want you to really understand what's happening here. So pi 2 twiddle, pi 6 twiddle, again, that's the coloring induced thing. what I did is I really just wrote down this right here. And technically speaking, when I write down pi 2, it doesn't really matter that that C1, look, I don't even really need to write down this thing right here because C1 doesn't get moved at all by pi 2 twiddle. So you can basically ignore it, which is why it's not appearing here in this first part right here, okay? And then what about this second thing right here? So you just, I'm gonna have you trust me that this is what you get if you actually apply pi 6 to all of the colorings. You end up getting this for pi 6 twiddle. Now, let's kind of talk through what happens with this. Where does C1 go? Okay, where does C1 go in all of this? Well, look, you apply it from left to right. Does C1 get moved at all by this first thing? No, it's fixed. What about by this? No. So C1 doesn't go anywhere, right? And that's why it doesn't appear over here. What about C2? What happens with C2? Well, C2 gets moved to C3 by pi 2, applying pi 2 first. C2 gets moved to C3, and then C3 goes to C4. So again, what happened overall? C2 went to C3, okay? And, all right, so I'm applying pi 2 to C2, and that moves me to C3. But then I have C3 and pi 6 operates on it now. And where does that go? To C4. So overall, what happened? C2 went to C4. And then we say, okay, before we close this thing off, we should ask where C4 goes. Well, okay, we apply it from left to right. C4 goes to C5, okay? And then we're done with applying pi 2. And then where does C5 go? Back to C2. So overall, C4 went to C5, went to C2. So overall, C4 went to C2. That's what the effect of pi 2 twiddle, pi 6 twiddle is on C2 and C4. It just flops them back and forth, okay? So if you go through and you do that with all of these, let's just do one more just for good measure. Where does C3 go? Okay, let's think about C3. Okay, if I apply pi 2 to C3, if I apply pi 2 to C3, it goes to C4. Okay, and so pi 2 is done operating. And then where does C4 go? Back to C3. So overall C3 went to C4, which went back to C3. So C3 is gone. The coloring C3 is fixed by this thing, which is why it doesn't appear here. Okay, so you end up with this right here, which is interesting. But I also could have figured out what this thing is by just thinking about pi 2 and pi 6 as permutations. Okay, I could think about pi 2 and pi 6 as permutations. And for this, let me kind of copy this down and then we'll work on this together. Okay, for this, okay, so pi 2, pi 6 is equal to A, B, C, D. And what is pi 6? Pi 6 flips A and D and B and C. And B and C. Okay, let me go ahead and share this with you. Okay, here we go. It's coming up here. We'll kind of figure this thing out in just a second. Okay, here it is. Okay, so how do I figure out what permutation this is? Well, remember we applied this thing left to right. Okay, left to right. So where does A go? So A goes where? Okay, if I apply pi 2, where does A go? Again, pi 2 is right here. Okay, so this guy right here is pi 2. And this guy right here is pi 6. Okay, well, if I apply pi 2, A goes to B. Okay, and that's what pi 2 does to A. But then what happens? Now I need to apply pi 6. Okay, so where does pi 6 send B? Okay, so pi 6 sends B to C. So overall, what happened? Okay, A, think about it. Where did A go when I applied pi 2, pi 6? Okay, it went to C. Okay, so let's kind of write that down. So A went to C. Okay, now what happens when I do this with C? Okay, just to make sure we're on the same page. Where does C go? Okay, well, if I apply pi 2, okay, where does C go? Well, C goes to D, okay, and then if I apply pi 6 after that, where does D go? Well, that goes back to A, okay? So, lo and behold, pi 2, pi 6, applied in that way, takes C back to A, so this thing gets closed off. So A and C are flipping back and forth, okay? So what about, let's see, what's something that we have not visited yet? Well, how about B? Okay, well, if I apply pi 2 to B, what do I get? Well, it goes to C. And what happens with pi 6? If I apply pi 6 to C, that goes to D. Okay? So what we do is we go like this. Okay? So, oops, no, that's not right. Sorry, pi 2 sent B to C. So that's all it did. And then we moved to pi 6. Where did C go? Well, C went to B. Oops. C went back to B. Okay, so B went to C and then C went back to B. So look, B is gone. B doesn't do well. B just kind of goes to itself. Okay. Okay, what happens when I apply? Okay, so B goes to itself. A and C went back and forth. What about D? What do you think is going to happen with D? Well, if I apply pi 2, what happens? It goes to A, and where does pi 6? What does pi 6 do after that? Okay, so pi 2 sent D to A. What does pi 6 do? Well, A goes back to D, right? So it's like this. Okay. Okay. And what permutation was that just flipped A and C back and forth, right? So let's just kind of remind ourselves here. Okay, here was A, B, C, and D. Okay, so flipping A and C back and forth like this. Okay, so that was reflection across the positive axis. Okay, I think that was the very last one that we had. So that was like pi 8. Okay, pi 8 is what that was. Okay, so again, you just kind of, you apply these things in a left to right fashion. And incidentally, that is not going to be very good notation, as I'll show you. I have to do some kind of weird things here in a minute. But that's okay. You know, we can handle it. It's all right. Okay, so back over to here. Let's go back in here. Okay, so what did we have? Pi 2, pi 6. It just ends up being AC, and B and D were both fixed. And indeed, if you take this permutation and then you look at all the colorings, you know, pi 8 induces, so the flipping of A and C back and forth induces this as a permutation. It induces this. And by the way, you know, that's exactly the same thing you would have gotten if you would have just taken the colorings themselves and operated them together. By the way, you call this composing. This is a composition of these permutations. Okay, you are composing them as functions, basically. You're letting the one operate and then the other after that. But that's where it gets iffy, because you know, normally when you compose functions, if you write them in a left to right way, you kind of, you think of applying the innermost function first and then the outermost one. But the way they do it in the book is they're always applying the leftmost function first and then the rightmost, whereas in most function composition, you apply the rightmost function first and then the leftmost. Okay, so that's confusing. So what do we mean by equivalent for colorings? We define the equivalence relation Ci is equivalent to Cj if there exists a permutation of the square such that pk twiddle of Ci is equal to Cj. Okay. So like there's a notation we're going to use. We're going to say G is the set of symmetries that make this an equivalence relation. Okay. Okay. So to make twiddle an equivalence relation, first of all, we need to know that if we compose two of these things, like we operate them together, composition, remember this is always left to right composition, okay? Whenever we operate those, we better get something that is once again a symmetry. G is the collection of symmetries. We call that closure, okay? We need to have something that fixes every element. This is just, this is just so that we can make sense of operating these things together, okay? So there's something called the identity that when you compose it with any of the other permutations, you just get that permutation right back. So if that happens, then, oh, by the way, right up here, I didn't write it this way. I wrote it, like this thing applied to this is Cj. So I'm thinking of this in function notation. But since they always want to do things in a left to right fashion, from this point on, I'm going to be having these permutations operate on these colorings on the right so that we don't get confused and like and accidentally slip into composition mode and compose things in the wrong order. Okay, so let's just read this sentence right here. Note that this condition forces, okay, pi e, so pi e is the identity element, pi e twiddle applied to C is equal to C for all colorings. For if it was the case that pi e twiddle, remember pi e is a permutation, pi e twiddle is the thing that is induced, or it's the permutation of colorings that's induced by pi, right? So don't forget about that. I'm using this twiddle notation, just to be more rigorous. That induces a permutation on the colorings, okay? Because if pi e twiddle of some coloring was equal to some other coloring, and pi k twiddle of Ci was equal to Cj, then what would happen to this? Okay, so let's try this out. This is our first time to use our newfangled notation. What would pi k twiddle of Ci be? Well, that would just be Cj. Okay, so you replace this thing with Cj. Now what's pi e twiddle of Cj? Okay, that's equal to Cl. Okay, so this thing applied to Ci gives us Cl, but that is not the same thing that pi k of twiddle of Ci is, after all, because that's Cj, and Cj is not the same thing as Cl. So that means that pi k twiddle, pi e twiddle is not the same thing as pi k twiddle because they did not send Ci to the same place, right? Pi k twiddle, pi e twiddle sent Ci to Cl, whereas pi k twiddle sent Ci to Cj, which is not Cl. So that would violate these things being equal, right? So it's necessary, right? If this thing satisfies that it fixes all the permutations, then the permutation it induces on colorings fixes all colorings. Okay, so that's just kind of an interesting little factoid. Okay, so we need closure, we need an identity element, okay, and we need inverses. Okay, so that is anytime you give me one of these symmetries, there is an inverse symmetry that kind of undoes what the other did. That's what an inverse is. It undoes what the other did. And basically, that's why we need the identity element. We need to make sense of what that means. That just means if I operate these things together, if I compose these things, what do I get? Well, I get the identity thing, okay? So, you know, these things right here, I'm not going to talk specific. So I'm not going to talk specifically about all of this stuff. This stuff's all pretty intuitive, but they do use a lot of the equivalence relation stuff that we want, right? But these are just some basic facts that we need to be true. We need closure. That is, we need to know when we operate these things, we land right back in the set of symmetries. We need a do-nothing symmetry called the identity. And we need, if we have a symmetry, we need to have a symmetry that undoes what the other did, okay? And incidentally, this is where Dr. Fry starts to get really excited. This is actually called a group, okay? Here, the operation is composition, okay? So a group is simply a set with a binary operation. Oftentimes you write dot for the operation and you even call it multiplication. But here our operation is composition, okay? But this is called an abstract group, okay? The set of permutations under composition is also a group, okay? We have an identity, we have closure, if I compose two permutations, I get a permutation. And we have inverses. It's easy enough to think of something that's going to undo what something did, okay? All right, so this is kind of our first little theorem that I want to talk about, okay? If G is a group of permutations of the set S, okay, so the set S could be corners of the square, and T a collections of colorings of S. So, okay, so T are the colorings, and S are the corners, okay? And by the way, eventually S will be things like edges. We'll color edges as well, you know, just for kicks, okay? So then G induces a partition of T into equivalence classes, okay? This is kind of what we were trying to make rigorous upstairs, right? G induces a partition of the colorings. Remember, T are the colorings, okay? G induces a partition of T into equivalence classes with the relation. C is equivalent to C prime if and only if there exists a permutation in the group that, right, whose induced permutation on the coloring sends C to C prime. Okay, I mean, this is really kind of the intuitive end of everything that we've been talking about here. If we want to actually make everything that we're talking about rigorous, you know, we need to talk about, okay, so what do we mean by equivalent colorings? Well, I mean this collection of permutations that I have is able to move me from the one coloring to the other coloring. Okay, that's what this thing is. Okay, so here's a little lemma, and I'm gonna end with this lemma, and then we'll get into the next section next time. Okay. Incidentally, this stuff with groups, this is Dr. Fry's bread and butter. He loves groups. That's what he deals with all the time. He's a group theorist. Okay. So here's a lemma. Suppose that I have two permutations in my set of symmetries, or in my group, if you will. Then there is a unique element pi, so pi ai, pi j are in G. Then there's a unique pi k in G such that pi I operated with pi k gets me to pi j. And moreover, pi k is just pi I inverse pi j. Okay, so we can actually figure out what pi k has to be. So that is, you hand me two permutations, right? You hand me two permutations, then I can basically give you an element in the group that moves me, right, such that if I compose pi I with that thing, it's really just pi j. Okay, that's actually more important than you might realize. And by the way, this thing is unique. Okay, so the proof has two parts. There's an existence proof. Okay, so first of all, you know by one of the axioms above that the inverse of pi I exists. Okay, the inverse of pi I exists. And by the way, technically we didn't write it down as one of the axioms upstairs, but technically speaking, we also need this operation of composition to be associative so that I can reassociate, reparenthesize, and not worry about getting different things. Okay, but what about existence? Okay, so I want to show that there is something that I can operate pi I with that moves me to pi j. Well, let's try this thing out right here, pi I inverse pi j. Well, then I can reparenthesize. What is pi I inverse? Well, it's the identity. Okay, and what's the identity operated with pi j? Well, it's pi j. Okay, so pi I times this thing or operated with this thing gets me to pi j. So I have found something that works. That's existence. Well, what about uniqueness? Well, let's prove uniqueness. What we would have to do to get uniqueness is we would go pi I pi k. So, assume that pi k, operated with pi I gets me to pi j, but also that pi I operated with pi k prime gets me there. Well, that means that pi I pi k is equal to pi I pi k prime. Okay, so those are equal. So what am I going to do? Well, let's just operate on the left by pi I inverse. And if I operate on the left by pi I inverse, I can reassociate. And of course, these guys are just the identity. But what's the identity operated with pi k and the identity operated with pi k prime? Well, that's just pi k and pi k prime, so they're the same. Therefore, this thing that moves us from pi I to pi j, okay, so that is pi I and pi k, if I operate them together, it moves us into a different permutation, namely pi j. That thing is unique. We can do it, and it is unique. And it turns out that's going to be a pretty important fact for us. Okay, so all of this abstract nonsense right here is really trying to do the job of making equivalence of coloring something rigorous. Okay, hopefully that stuff kind of makes sense. And again, hopefully it makes sense why I'm using the twiddle notation, why I'm operating permutations on the right of the colors because of the way the book always wants to operate from left to right, and so on. Okay, so hopefully that makes sense. And next time we will start talking about something called Burnside's theorem. With all of the setup that we've been doing in 9.1, we're now going to be ready to try. Remember what we're trying to do. We want to ultimately count the number of equivalent. Right, we want to count colorings that are non-equivalent. In this case, there were six non-equivalent colorings. There were 16 total colorings, but lots of them fell into equivalence classes. Now we have a rigorous idea of what an equivalence class means. It just means that, these permutations are moving me around among them, okay? And we want a way to actually count the number of those equivalence classes. That is going to be the number of distinct colorings, okay? And that is what we will talk about next for now.